All right, we're going to look at section 4.3, which tells us what derivatives tell about the shape of a graph. Now, the first part of this, we're going to look at increasing and decreasing, which is what the first derivative tells us. If you recall, for a function f of x, if we evaluate the first derivative, f prime at c, that tells us the slope at the number c. So if the slope's positive, the function's going up. If the slope's negative, the function's going down. So that's what lets us tell if the function is increasing or decreasing. And this is a nice fact here. The only places where a function can change from increasing to decreasing or vice versa is at a critical number. So what we want to do to figure out where the intervals of increasing and decreasing are is first you find all the critical numbers. Then you cut out the real number line at the critical numbers. And since those are the only places where the sign can change, all you have to do is pick a test value inside each one of those intervals and then see if the derivative is positive or negative there. Remember, critical numbers happen in places where the derivative is 0, like this, or in places where the derivative is undefined, where you have a sharp corner, maybe something that looks like that. So let's do an example. All right, first up, find the intervals where this cubic function is increasing or decreasing. Okay, so let's find its derivative. Derivative is f prime of x is 6x squared minus 4x minus 7 over 2. And now we want to set that equal to 0 and solve. So set it equal to 0. I could try to factor this. I'm not going to, though. Instead of factoring, I'm just going to jump straight to the quadratic formula. So I get 4 plus or minus the square root of b squared, so that's 16 minus 4 times 6 times negative 7 halves. And all that stuff over 2a, so 2 times 6. Now if I grab my calculator and plug in that stuff, let's see, 16 minus, or actually I'm just going to do plus 4 times 6 times 7 over 2, and it gives me 100. So 4 plus or minus square root of 100. Of course, you know what that means. Since we got a perfect square under there, it would have factored, and it would have factored fairly nicely. But let's don't worry about that. What we get here is 4 plus 10, or 14 over 12, or 4 minus 10, negative 6 over 12. So it looks like our critical numbers are 14 over 12. Let's rewrite that as, I'll tell you what, let's use decimals. 14 over 12, that's not 1.4. What am I thinking? 14 over 12. It's 7 over 6. Let's not use decimals. So that's 7 over 6. And negative 1/2. I'm going to put a box around that because that's the answer to the first step. Now we need to cut up the number line. Cut the real number line into intervals at the critical numbers. So what I'm going to do is come over here and draw my real number line. I'm going to cut it up here at negative 1/2 and positive 7 over 6. Now, don't put any additional numbers on there. Don't put, some people say, here's my number line, put 0. Don't do that. The only numbers you want in here are the numbers where you're cutting it up. And then in each one of these areas, intervals, we're going to pick a test value. I'm going to write those in, and I'm going to do those in green. So it's natural to put 0 in the middle, since that's the easiest number there is to plug in. Let's see, 7 over 6, that's bigger than 1, so let's pick 2 to go in this interval. And back here, negative 1 would go in this interval. Now, you can pick any number you want in the intervals, but generally, you want to pick the ones that are going to be the easiest to plug into the derivative. Now, I'm also going to come over here and I'm going to draw some lines up here. These are the only things I'm going to draw. Don't put a tick mark above your numbers, your test values. You're not cutting the thing up there. You're just cutting it up at the critical numbers. But now I'm going to come over here and I'm going to evaluate f prime of each one of my test numbers. Okay, so f prime of 0, that one's going to be easy. You plug 0 into here, you get negative 7/2. So f prime is negative. All I'm going to do is put the sign in this chart. F prime of negative 1, that's going to be 6. Then plus 4 minus 7/2. Equals, I don't really care what the number is. All I care is that it's positive. And for 2, that's going to be 6 times 4 minus 4 times 2 minus 7 over 2. So that's 24 minus 8 minus 3.5. That's positive. All we care about is the sign, because that tells us what the function does. So f over here is increasing, then it's decreasing, then it's increasing again. And I'm getting that from looking at these the signs of the derivative. Now, this lets us do a couple of things. I can write out the answer. The question asks, find the intervals where it's increasing or decreasing. So this thing is increasing on the intervals where the derivative is positive, or where it's going up. So it's increasing on minus infinity to minus 1/2, and from 7/6 to infinity. And it's decreasing on the interval from negative 1/2 to 7/6. So that's my answer. Now, if I ask you to do this on a test and I tell you to show your work, this is what I want to see right here, this chart. So that is what I would want you to show. Now, there's one other thing I want to talk about here. We're done with this problem. Actually, tell you what, let's do. Let's look at it on Desmos. Find the intervals where this is increasing or decreasing. I've got it already put into Desmos here. If you look at the function right here, this is the function. Let's call it f of x. So there it is. And notice it's decreasing from here to here. And notice those x coordinates. This one up here is negative 1/2. What did I say? Yeah, it's decreasing from negative 1/2 down to 1.167. That's 7/6. And if we put in f prime of x here in green, notice that shows us really what our chart shows. It's positive until you get here to 1, or I'm sorry, not 1, to negative 1/2. Then it's negative until you get over here to 7/6, and then it's positive over there. So this chart is really just sort of an outline of what the function looks like. Well, and that leads us to what's called the first derivative test. Let me get this off of here so we can see it better. This gives me an idea. I'll do this with a highlighter. It gives me sort of an idea of what the function looks like. So from looking at this, we can look at it and say this function has a relative max at x equals negative 1/2 and a relative min at x equals 7/6. And that's called the first derivative test. And the details of that are written out right here. Notice it says if the derivative changes from positive to negative, then it has a local minimum, or local maximum. And that's what's going on here. The derivative changes from positive to negative, and you've got a max. But I don't really think about changes from positive to negative. I don't memorize that stuff. I just draw in a nice curve here with these arrows, and that tells me what's going on with the function. I guess there is one other thing worth doing. On our chart, the derivative is 0 here. I guess I'll do this in green. The derivative is 0 here, and it's 0 there. So that way we know that it has a nice smooth, rounded max and rounded min. If the derivative were undefined, that would mean it would be more of a point, a sharp corner or cusp. So on the rest of these examples, we're asking two things. Find the intervals where something is increasing or decreasing, and find the local max and min. And basically, once you've done the increasing and decreasing part, finding local max and mins, there's not much more work there at all. So I want to do several more examples, but I'm going to start those in the next video.